I'm going to continue with the discussion of the impacts of climate change. I showed this one before. Today I'm going to talk about the impacts of climate change on aggregate welfare, and then next week I'm going to talk about the distributional impact. There's been 27 estimates of the total economic impact of climate change. They are displayed here as the blue dots. And the way to read this graph is as follows. On the horizontal axis we're looking at scenarios of climate change here indicated by the change in the global mean surface air temperature since pre-industrial times. So that is what is displayed here. And then on the vertical axis we're looking at the welfare equivalent income change. That's shown here. The way to read this graph is that if you focus on the scenario of 2.5 degrees of warming, then that would make the average person, so the way to read this is as follows: 2.5 degrees of global warming would make the average person feel as if she had lost 1.3% of her income. And 1.3 is the average of the blue dots that you see around 2.5. Before I'm going to interpret what is going on here, I'm first going to talk about where the numbers come from. There's been a range of methods used to derive these estimates. The most common one is the so-called enumerative methods. I think it was Bill Klein who coined this term, but it was really Ralph Darts who first did this. And essentially what you do there is you go through all the impacts of climate change one by one, roughly like I did yesterday. You sort of come up with estimates of the change in the quantities, essentially. Physical change, the number of people dying, the kilometers of dike that you need to build, and so on and so forth. And you estimate the price of these things, you multiply and add up. And it's as simple as that. Now, for some of these prices, it's relatively easy to come up with what is the value of something. For instance, if you want to know, you're going to raise the dikes around East Anglia, what would that cost? Essentially, you call up an engineering company and say, what would it cost to raise a kilometer of dike by 1 meter? Right? And they will give you an answer that would probably be in the order of 6 or 7 million. And then you multiply the two and you add them up. It's as simple as that. For other issues, it's not as easy to estimate the price. For instance, what is the value of butterfly species going extinct, or what is the value of somebody dying prematurely because of climate change? You need to use valuation methods. So last term George talked about these methods. There's a revealed preference method, which are fairly robust but fairly limited in their scope, in the sense that they can only assess consumption values of things, direct consumption values of things. And then there's the stated preference methods like contingent valuation, contingent choice, which can be applied much more widely. They can be used to assess the value of existence values and bequest values and option values and what have you. But the big problem there is that they're stated preferences rather than revealed preferences. You essentially do not ask people to pay for the good or service that you're trying to value, and therefore they can give any answer. They may lie deliberately or they may simply not know the answer and give you one nonetheless. In these valuation studies, there's two things that are particularly relevant for climate change. And one is the distinction between the willingness to pay for a good or service and the willingness to accept compensation for the loss of a good or a service. And there are essentially two different policy scenarios. The willingness to pay, essentially as if you're going to a supermarket and you're buying something. You give up part of your income in order to gain something that you need or want. Willingness to accept compensation is a different scenario. You own something and now you're losing it and you're getting paid compensation in return. Now, what you would expect, based on the first principles of micro, is that willingness to pay and willingness to accept compensation are very, very close to one another. And there's a theoretical paper by Willy which shows that willingness to accept compensation, which is technically known as the compensating variation, is always bigger than the consumer surplus. This is the approximation that we usually use, and the consumer surplus is always greater than the equivalent variation, which is a technical term for willingness to pay. But Wieler also shows that the three must actually be very close together. And the reason that they're not is essentially because of the income effect. So willingness to pay, you give up something, some part of your income to acquire something. Willingness to accept, your income essentially goes up, right? So for instance, you may be considering to buy a coffee mug, right? And say that's going to cost you £5. Then £5 is your equivalent variation, and then your compensating variation is, suppose you have a coffee mug and you drop it, how much would we need to give you to compensate you for that loss? The answer would be roughly £5, right? Of course, one has a different income constraint than the other, because in the two scenarios, the difference in income is £10, right? But that should not lead to a large difference. That is what you would think, right? That is what standard micro theory would tell you, that equivalent variation and compensating variation should be very close together. Willingness to pay and willingness to accept compensation should be very close together. Now, there's been tons of experiments on this, and the result is shown here of an earlier set of experiments. Now, if the willingness to pay equals the willingness to accept compensation, then you would find a 1. Here, if the willingness to accept compensation is larger than the willingness to pay for equivalent good or service, then it would be greater. And what you see is that there's been measurements in the literature where the willingness to accept compensation exceeds the willingness to pay by a factor of 10 or more. There's also been a few studies where it's actually the other way around, but they are decidedly in the minority, right? And what you're looking at here is the frequency of observation. So now, how come? Why are these two values so very different? Essentially, we're valuing the same thing, you would think, right? And there's a number of reasons that have been forwarded in the literature. The one, going back to Wieler, is that the budget constraint is different. For willingness to pay, if you're buying something, you are constrained by your income. Willingness to accept compensation, you are constrained by the income of the compensator rather than by your income, and that may explain the difference. But that cannot explain the full difference. So they've done these experiments indeed with coffee mugs where there's a group of students in a room, and half of the students in 2 rooms, right? In 1 room, students were asked, what would you pay to buy this coffee mug? And they said £5, because that's what it costs in the shop downstairs, right? And in another group, students were given a coffee mug and then they were taken away again. And they were asked, so how much do we need to give you to compensate you for your loss? And then all of a sudden, even though the students knew that in the coffee shop in the shop downstairs they could buy a coffee mug for £5, they said, give me 10, right? And sort of, even if they had not have had time to sort of acquire an emotional attachment to the coffee mug because they've just been given it 5 minutes prior, they would still say, give me 10. Now, I think that the explanation for this particular experiment is a resentment of students towards their professors. Essentially, you give them something and then you take it away again, and students get cross when you do that, and they want to be compensated for that, particularly when it's done by an unpopular professor who teaches microeconomics. And that is probably where the real explanation lies. It's more in the psychology of things. And there's 2 important things here. One is that there's a difference in people's minds between voluntary risks and involuntary risks. If you get drunk, you get into a car, you get into an accident, you lose your leg, that is bad, right? If I get drunk, I get into a car, I get into an accident, and you lose a leg as a result, that is worse, right? Even though objectively the 2 scenarios are the same. You lost your leg. But people perceive harm being done unto them by others is worse as harm that they do to themselves. And that may be one of the explanations why willingness to accept compensation is much larger than willingness to pay. And this is immediately relevant for climate change, right? Because climate change is not something that we do to ourselves. The current climate change is caused by the actions of our parents and grandparents. And similarly, future climate change will not be done to future generations unto themselves, but it will be done because of our emissions, right? Not because of their emissions. So climate change is an imposed risk, and it's involuntary for every generation. So that may be an explanation. The other explanation is that people are loss averse, that people attach value to the status quo. And one valuation scenario there may be something as follows. Suppose that you live near a parking lot and somebody comes knocking on your door and says, we are thinking of converting this parking lot into a park, and it will have grass and trees and fountains, and it will be all very nice, much nicer than the concrete and cars that are there now. We have convinced the municipality to give us permission to do so, but we haven't convinced them to fund this, so we're raising funds to make this conversion. How much would you be willing to chip in, right? That would be one scenario. That would be willingness to pay. Willingness to accept compensation would be somebody comes knocking on your door and says, you know that park down the road, right, with the grass and the trees and the fountains, they are thinking of converting it into a parking lot, but they realize that this is going to cause a welfare loss to you. How much should we give you so that you won't protest? Now you may think objectively the two are the same, right? It's concrete and cars versus versus grass and trees and fountains. But of course your memories of the place may be completely different, right? The park may be where you walked your dog for years. It may be where you kissed that girl or that boy. And you may have fond memories of this park. And therefore you may say, I want higher compensation, right? Of course also people have fond memories of car parks, right? So it may work the other way around. Because of this, the compensation that you would need to pay for imposing climate change is probably higher than our willingness to pay to get less climate change. And that is an important thing to consider. In all the scenarios that I'm going to show later, all the estimates that I'm going to show later are all based on willingness to pay. There's another important aspect about valuation methods that is particularly relevant for climate change, and that is that primary valuation studies are expensive. So your standard travel cost study, your standard hedonic pricing study would easily keep a junior researcher occupied for a year. Contingent valuation is more difficult and more expensive. So the costs of a single primary valuation study are easily £50,000, but can also easily become £500,000. Because of that, there are only a limited number of primary valuation studies. But what we need in order to assess the impacts of climate change is not that we know the value of Brighton Beach and the value of a particular forest, but we need to know the value of all beaches. We need to know the value of all forests. And we need to know the value of all species. So what we need to do is essentially extrapolate from those goods and services for which we have an estimate of their worth, and we need to extrapolate to all the rest. That is easily said, but actually it turns out that in practice this is very, very difficult. Let me just straight go to a particular example. This is from a study, a travel cost study in Denmark. What you're looking at is the value, the recreation value of all 57 forests that are in Denmark. And what the study did is it had travel data for 2 periods of time separated by 20 years, knew all the visitors, knew where they came from, knew how they got to the forest, knew how long they spent there, and so on and so forth. Pretty detailed data. And And then what it did, it estimated a value model based on 56 forests and predicted the value of the 57th forest, and then repeated that 57 times, right? So 56 observation, you predict the last observation, and did that over time. So 20 years later, could we predict what the value would have been? And this is, of course, roughly similar to what you want to do in climate change, right? So we observe values now, we want to derive what is the value of this thing in 2050 or in 2100, so you want to extrapolate over time. And then there was all sorts of characteristics that were known, so the age of the people and their income and their education and so on and so forth. And then there's two results shown here. One is the comparison of the predicted value versus the measured value in the later period, using a simple extrapolation where we assume that we did not know people's income and so on and so forth 20 years later. So that is this scenario. The second is the same difference between observation and prediction, but now updating. We don't know anything, but we don't know the value, but we do know how rich people have gotten in 20 years' time and so on and so forth. So this uses future information in its prediction. And what you see and what is displayed here is the error, right? And if the error is 0, the prediction is accurate, right? And there are a few cases where indeed the study was able to accurately predict the value, the recreational value of a Danish forest 20 years in the future. But you also see that actually in the majority of cases, vast majority of cases, the error exceeds 100%. And Denmark is easy, right? Nothing much changes in Denmark. So this is a prediction of Denmark in 1980 versus Denmark in the year 2000. Nothing much has changed. What we need to do for climate change is predict from observations in the UK in the year 2010 what would be the value of things in 2070 in Pakistan, right? That is the sort of stuff that we do for climate change. If you can't do Denmark over 20 years, what hope do you have to do the world in 100 years? Similar story here, and now these are US results. They are slightly better. You measure things in two places, all have to do with water. You predict what is going on in the other place. You compare it, and these are the errors that you make. They're occasionally small, they're occasionally very, very big. This sort of extrapolation is extremely difficult. So I talked about the enumerative method. You estimate the quantity changes, you estimate the price, you multiply the two, you add them up. There's an immediate drawback there, that is we ignore even partial equilibrium, right? There's a big change in crop yields, we assume that prices don't respond to that. It's a bit peculiar. So what other people have done is apply full-blown computable general equilibrium models where we don't only do the partial equilibrium, if the quantity changes, price changes as well in the same market, but also does the general equilibrium. If there's an impact in one market, in one country, then through budget constraints and consumer preferences and so on and so forth, competition on input markets, this impact would spill over to other markets as well. Computable general equilibrium models also have the advantage that, unlike the enumerative method, you can look at the interactions between impacts. So in the enumerative method, what people do is they estimate the impact of climate change on agriculture and quantify its impact. And then they estimate the impact of climate change on water resources and value the impact. And then they add up the two, forgetting that 70% of freshwater resources are used in agriculture. And computable general equilibrium models, you can also look at the interactions between impacts. So this is theoretically superior, it's harder to do, and therefore there's fewer estimates around. There's also studies that use statistical methods. And essentially what you do there is that you estimate the relationship between an economic activity or an economic quantity and climate. And you do that over space, and then you transpose this relationship and you assume that it holds over time. So the earliest example of this is where they looked at the value of agricultural land in the US. Red Ricardo, who wrote that all characteristics of land are sort of reflected in its price, including if you buy a piece of land, essentially you also buy its location. So if you buy a piece of land, you also buy the rain that falls on it and the sun that shines on it and so on and so forth, right? That sort of comes with the purchase of the land. And of course, a better climate is reflected in the price of land that would be used for agriculture, because that determines how well your crops will grow there. So they estimate this relationship over space and then say, well, let's assume that this relationship holds over time. There's two immediate drawbacks to this. One, a relationship over space is essentially a relationship that holds institutions constant and technology constant. If you look at the relationship between climate and agriculture and land values in the US, they're all in the US at the same time. They all have the same trade policy. They all have access to the same seeds, the same fertilizers, the same pesticides, the same tractors. But if you look over time, then trade policy changes, agricultural technology changes, and so on and so forth, and that may change the relationship between climate and agriculture. So that is one drawback. The second drawback is that it's easy to trade over space. So Maine specializes in lobsters, Florida specializes in oranges. It's not because people in Maine eat only lobsters and people in Florida eat only oranges, right? They trade and they both have a varied diet, right? Now that is relatively easy over space. Trade over time is very, very difficult, because essentially we travel in one direction at a constant speed in time. So that is immediately ignored. The big advantage of this statistical method is that you don't have to make assumptions about how people adapt to climate change. In the numerative method, in mutable general equilibrium studies, you have to make an assumption about how people respond. And I talked about it yesterday, that there's a lot of studies that assume that people are incredibly dumb, and that's actually analytically easy. You can also make the assumption that people are perfectly rational and very well informed. It's also analytically easy, but may not be a correct assumption either. The truth is probably somewhere in between, and then it becomes analytically very, very hard to deal with this. The statistical method looks at adaptation as is, right? We don't make assumptions about how farmers would respond to climate, but we actually look at how farmers did respond to climate, right? And then there's one study, and there's another one, should be forthcoming, where they just asked experts, what do you think the impact of climate change would be? I write here, experts. This study was done in 1994, when nobody could credibly claim to be an expert on this. So they asked people with titles and stuff rather than true expertise. And the result is, as you see here, despite the variance in methods, you actually see that people roughly agree, at least on the order of magnitude, right? So that is good. There's all sorts of things wrong with these studies. They're incomplete. For instance, the impact of climate change on tourism is still not included, whereas you can reasonably expect this to be a big one. You could both expect that the impact of climate change on tourism is big, because that is one of the main reasons why we travel to Spain in summer for our holidays, but also tourism, recreation, leisure takes up about 10% of global consumer spending at the moment. So also in economic terms, it is actually a very big sector, but it's not included yet. Some of these studies ignore the interactions between impacts. I said it already. Some of these studies have a very stylized form of adaptation. That's what I said already. Most of the impact studies focus sort of on what is going on in the middle of the probability range. There's very little emphasis on low probability, high impact studies. Indirect impacts, the effects of climate change on economic growth, the effect of climate change on violent conflict have all been basically ignored. Evaluation methods and basically all our economic and other modeling tools are all sort of reasonably good quantifying the impact of small changes. But here we're not talking about small changes, we're talking about large changes. And it's fairly easy to value or to estimate the value of a particular forest. It's much more difficult to value all forests and a wholesale chain, say from needle leaf to broadleaf. That's much more difficult than saying, well, what would happen if I cut down this particular forest? Nevertheless, this is what we have. Now, there's a number of lessons that can be drawn from this. The first is the order of magnitude. And as I said, if we focus on 2.5 degrees of warming, then what we would see is that if we take the average of the studies that are out there, then 2.5 degrees of warming would be equivalent to losing 1.3% of your income. Now, 1.3%, losing 1% of your income is not something that you should worry about. It's not a problem, but it's also not very big, particularly when you consider that 2.5 degrees of warming would take 50, 60, 80 years. So one way of rephrasing this is that a century of climate change is about as bad as losing 1 year of economic growth, which immediately makes that climate change is not the biggest problem of humankind. There are a lot of clowns in the media out there who claim that climate change is the biggest problem of humankind. It's just not borne out by the numbers, right? I mean, people in Greece lost about a third of their income in 5 years' time due to the beloved monetary union, right? Which is much bigger than losing 1% over 100 years, right? Or 2% over 100 years. And of course, the people in Syria wish they had the problems of the people in Greece, right? So it's not very big. That's the first thing. And it's not only that climate change is not the biggest problem of humankind, it's also not even the biggest environmental problem. Projections of the death toll because of climate change runs into perhaps 1 million premature deaths by the end of the century. About 4 million people die of urban air pollution per year now. Another 4 million die of indoor air pollution now. Of course, if you're comparing 1 million in 100 years versus 4 million now, then you would have to say the 4 million is the bigger problem, right? So climate change is also not the biggest environmental problem of humankind. So that is the first thing you notice. Second thing is that the initial impacts of climate change may well be beneficial. And that is because of CO2 fertilization. I spoke of that yesterday. It has to do with reductions in cold-related mortality and morbidity. I spoke of that yesterday. And also, of course, energy consumption in winter will go down. That is actually another benefit. But then, if you look further into the future, climate change becomes worse. Now, these initial benefits are no reason to start subsidizing carbon dioxide emissions and other greenhouse gas emissions. And that is because, well, first, this graph is relative to pre-industrial times. We've already seen about 0.8 degrees of warming over the last 1.5 century. So we are roughly here. So the turning point is actually very, very close. And because of all the momentum in the carbon cycle and in the climate, because of the ocean, as well as in the energy sector, we will not avoid this turning point. Right? We will have to work very, very hard to keep warming below 2 degrees. More likely we need to start counting on 3 or 4 degrees of warming. And the initial benefits of climate change are so-called sunk benefits. We will get them regardless of what we do. If you would stop all emissions today, then the world would easily warm another degree or so. So the initial benefits are sunk benefits. They're irrelevant for policy. And that's the second message. The third message is the uncertainty of it all. Right? So I sort of pointed out that different methods that have been used, but they all seem to agree on the order of magnitude. It's a few percent of GDP, but at the same time, experts disagree on the sign, right? Which sort of tells you that we should not be too confident about the results. There's also only 27 estimates, which also does not inspire a lot of confidence. And then, of course, you should know that these people actually know each other very, very well, right? So there may be groupthink, there may be undue influence of one estimate over the other. But even with that limited information base, if we focus on the confidence interval, then you see two things. One, that the confidence interval is wide, and second, that it's skewed in the wrong way. That is, negative surprises of equal probability are larger than positive surprises. Or phrased differently, to say that the skew is the wrong way and the right tail is heavier than the left tail. And that goes back to emission scenarios. And it's much easier to imagine a world where there's high carbon dioxide emissions than to imagine a world where we rapidly transition to carbon-free technology that has to do with climate sensitivity. If you look at subsequent IPCC reports, what they always say is that the best guess of climate sensitivity, that is how much the world will eventually warm if carbon dioxide in the atmosphere were to double, is 2.5 degrees, but then the range of uncertainty is 1.5 to 4.5, right? So also there you have that negative surprises are more likely than positive surprises of equal magnitude. And ditto for the impacts. Most of the impacts are more than linear in climate change, so you would expect things to escalate. And it's much easier to imagine a world where things go dramatically wrong because of climate change than things go dramatically right because of climate change. Nobody has written ever that we will all be blissfully happy because of climate change, but people have written stories about how things could go dramatically wrong because of climate change. Sort of the most dramatic impact that has been predicted is that the planet would overheat and explode. I would not believe that. It has been published in a peer-reviewed journal. But you can easily imagine dramatic scenarios. My favorite dramatic scenario has to do with sea level rise. If sea level rises and Bangladesh does not get its act together with regard to coastal protection, then about 30% of the landmass of Bangladesh would disappear under water within this century. That would mean that you have to, current population, you would have to evacuate about 50 million people. Future population, maybe 100 million people. You may wonder, where will these people go? They will have to leave the plains of Bangladesh. There's a few options there. They can move into the hills of Bangladesh. And the people on the plains of Bangladesh and the people in the hills of Bangladesh don't really like each other, and it's sort of been this low-level civil war brewing for a while now, so that may lead to conflict. But it's actually much more likely that a large number of these, say, 80 million Bangladeshis who have to move, will move into Pakistan. Will move into India, right? Now, relationships between India and Bangladesh aren't great. There's a lot of migration from Bangladesh into India that the Indian government is really not happy about at the moment. And you can imagine that a future large influx of Muslim refugees into a majority Hindu country would lead to some form of conflict. You can also easily imagine that the Pakistanis then say, we're going to come to the rescue of our Muslim brethren who are being slaughtered in India, and that would lead to nuclear war on the Indian subcontinent. All because of climate change. I'm not saying that this is going to happen, but at no point in this chain of events can you say, no way, this is not going to happen. And that means that there is a possibility, hopefully a very small probability, that things will go dramatically wrong because of climate change. This meter of sea level rise that would cause this is 70 years or more into the future. If you go back 70 years in time in Europe, 75 years in time in Europe, Europe was at the brink of war, right? Much like India and Pakistan have been on the brink of war for a long time. But Europe is no longer on the brink of war, right? So things may completely change in the future. It may be that all South Indians will get along very, very well in 70 years' time. They don't at the moment. So how likely is this? I don't know. But you cannot exclude it. Right? You just cannot exclude these dramatic scenarios. That is why we should pay close attention to what is going on at the bad tail of the impacts of climate change, which suggests perhaps, if we start accounting for this, that we should not compare a century of climate change to losing a year of economic growth, but perhaps to losing a decade of it. So far for the total impacts. Total impacts are nice to talk about, and they often draw a lot of fire, and they're also fairly irrelevant for policy discussion. For two reasons. Sort of the intuitive reasons is very simple. If you're in charge between two elections of a small country, there's no hope in hell that you can avoid climate change altogether. You sort of look at our span of control, even if you're Prime Minister of the UK, it is very limited. The best you can hope is slightly change emissions. So what you should be looking at, what is the impact of slightly changing emissions, rather than what is the impact of total climate change, as if you could take away climate change altogether. So that is the intuitive reason. The technical reason is, of course, that if you want to maximize something, then you take the first partial derivative, and really what we should be looking at, what is the benefit of reducing CO2 emissions by 1 ton. We should be looking at the margin rather than the total. And then, of course, we also recall PGU, that what we should be doing if we want to maximize welfare, then we should equate the marginal abatement costs to the marginal damage costs, right? And if we evaluate this along an optimal path, then we can call this the PGU tax. So it's much more relevant for all sorts of reasons to look at what happens in the margin rather than what looks at the total. What are the values that come out? There's been 27 estimates of the total impact of climate change. On last count, there were 1,231 estimates of the marginal impact of climate change. And at first sight, that seems strange, right? Because one is the first partial derivative of the other. And if we have 27 totals, and we take the first partial derivative, then we should have 27 partials. Now, the reason that there's 1,231 is not because economists don't know how to take a first partial derivative, but it's because there's many more degrees of freedom. So the 27 estimates are, if climate were to change by this quantity, what would the total impact be in a particular year for a particular scenario? Of course, there's many alternative future scenarios of emissions, and that immediately brings with them different paths of the impacts of climate change. There's many different ways of calibrating a climate model. There's many different ways of doing this and doing that. And then, of course, there's also, you have sort of a path of impacts in the future. The marginal damage cost, essentially, the way you calculate this is you have an emission trajectory and therefore a climate trajectory and therefore an impact trajectory. And then you slightly change the emissions in the year that you're interested in, say 2016. And then you calculate a new concentration path and a new climate path and a new impact path. And then you take the difference between the two and discount that back to today. And then normalize it with the change in emissions that caused the difference in impact in the first place. So immediately what you see is that the impact estimates also depend on the discount rate that you assume in your net present value calculation. But of course your impacts are not just for the world as a whole. You have impacts on all sorts of different countries. So also the way you aggregate these impacts across countries, and how you weigh the plight of poor people relative to rich people, and so on and so forth. All these things come into play. There's many, many degrees of freedom, and that explains why we went from 27 estimates to 1,231. Now, if you have 1,231 estimates, you can do all sorts of fancy things, including kernel density estimation, and that is what you see here. What you're looking at is the cumulative density function of estimates of the WTAC, so the social cost of carbon. And in black, that's just all 1231 put together. The way to read a CDF, for those who forgot, is as follows: that if you look at $300 per ton of carbon, then there's a 50% chance that the social cost of carbon or the WTAC is above that, and then consequently there's also a 50% chance that it should be below that value. Right? If you have so many estimates, you can also do sample splits, and then you begin to learn more than just there is a CDF. And the sample split that is shown here is between different values of the pure rate of time preference, and I'll come back to that in, I think, 5 or 6 weeks' time. What I mean by that is essentially the discount rate. And the way to go from the pure rate of time preference to the consumption discount rate, the money discount rate, that's what you're used to, better used to, is to add 2, right? So this is a 5% discount rate, a 3% discount rate, and a 2% discount rate. And what you see is 2 things. First, if you just focus on the median, so the 50% in the cumulative density function, then for a high discount rate, the median is around, what is it? It's 30, 35. For a 3% discount rate, it goes to about 150, and then for a 0%, for a 2% discount rate, it goes to 475. And this is intuitive, right? The higher the discount rate, the less we care about the future. The less we care about the future, the less we care about climate change, which is a future problem. And you see that quite dramatic sensitivity of your numbers to the assumed discount. There's another more subtle thing that you see, and that is that the CDF is much tighter for a higher discount rate. So here it starts at 0 and it ends at 1, as a CDF should. If you look at the 0% one, it doesn't start at 0, it doesn't go, it goes to 1, but it's somewhere way out in the downs, right? Before it reaches 1. And the reason for this is also intuitive. The lower your discount rate, the more you care about the future. The more you care about the future, the further you need to look into the future. And the further you look into the future, the hazier things become. You guys have a reasonable idea about what you're going to do this afternoon, right? That's fairly certain, but things that you will do in 10 years' time or 100 years' time are pretty, or what the world will look like in 100 years' time is very, very difficult. If you go for a very low discount rate, if you follow Nick Stern's advice and say we should be using a very low discount rate of about 0.1% pure rate of time preference, then you need to look 12,000 years into the future in order to properly estimate the social cost of carbon. Who knows what the world will be like in 12,000 years' time? I don't. If you look back 12,000 years, the world was completely different then. So this is the CDF. Here are some characteristics. Mode, median, mean, standard deviation, essentially the same story. If we just focus on the 3% pure rate of time preference, 5% discount rate, roughly what we use for other public policies, I'll come back to that, then we would recommend a social cost of carbon of around $40 per ton of C, which by happenstance is roughly equal to the 6-7 euros per ton of CO2 that you would pay for emission permits in the European trading system for those permits. This is the probability density function. There's 2 things here. This is all for a 3% pure rate of time preference and 5% discount rate. There's 2 distinctions that 2 messages here, and then I'll shut up. One, the difference between, so in blue we're looking at all estimates. In green we're looking at those that were evaluated along a business as usual scenario, a scenario without climate policy. And then in red you're looking at those scenarios where the carbon tax that was estimated was also imposed, and therefore emissions fell, and therefore climate change is not as big a problem because emissions are lower. And what you see is that indeed, if we do not just estimate the carbon tax, but also impose the carbon tax, and then we slightly shift to the right, that is, we would impose a carbon tax that is slightly below our estimate of the social cost of carbon, but the blue and the green, of course, have a lot of overlap in their support. The other thing that you notice is that also here the bad tail is fatter than the left tail. It's just a greater chance of a negative surprise rather than a positive surprise. That also plays out in the uncertainty about social cost of carbon. And the final thing that you see is that actually imposing the carbon tax has two effects. One, it shifts the mode towards zero, as you would expect, because emissions are lower, but it also actually fairly dramatically thins the tail, the bad tail. So you take away a lot of the negative surprises by imposing even a modest carbon tax. So that is all for today. We talked about the impacts of climate change. We find the benefit of climate policy as the avoided impact. I hope you do not walk away with this, with the idea that we know these things fairly well, right? There's an enormous amount of uncertainty, there's an enormous amount of assumptions that go into this, and I also hope to have given you the message that some of this is positive in the sense of what if, but there's also a lot of normative elements, and I particularly talked about in this country, this of course is subject to huge debate.